Hello Math 2 and welcome to week 10 where we're doing something called curve sketching. This is sort of an old-fashioned way to say what we're doing. We're basically describing what the function is doing. So take a look at this example. So with this function, there's several things going on. So one thing you'll be asked to do is find the x-intercept. And when we actually get down to it, you would actually just have the function, not necessarily the graph. And then we need to go through and find things like the x-intercept. So there's an x-intercept at x equals -1. Right here at 2, that's the y-intercept. So there's a y-intercept where y is equal to 2. Right here, there's a maximum value when it reaches the top of this little hill. So this would be x is 1 and y is a 2.5. So there's a maximum at x is 1 and y is 2.5. And over here, there's a minimum. And both here, the derivative would equal 0, and here the derivative would equal 0. And this one is a y value of approximately a half. So there's a minimum when x is a -3 and y is a half. Then we're also going to find out the domain, and that's the possible x value. So right here, the function is undefined with that red asymptote. And so the domain would be everything except -2. And also there's a vertical asymptote. So vertical asymptote at the x equals -2. So this is saying the function is undefined, so you can't have x equals 2. And then this is saying where's the red dotted line? The red dotted line is where x equals the -2. And then this red dotted line is a horizontal asymptote, and that is where y equals 1. So then there's also a horizontal asymptote where y equals 1. And with some of the homework questions, they'll ask for maybe a couple of these things, and with a few of the homework questions, they do ask for all of them. But let's get started. So the first thing that I'm going to do is actually find this, the horizontal asymptote. There's this easy and fun rule called L'Hopital's rule. So L'Hopital was French. That's the reason it's spelled this way. So it's got a silent H, L'Hopital's rule. And it goes like this. Suppose you're taking the limit and you've got a fraction, one thing divided by another. And the limit could be going to whatever. That's not really the important part. The important part is, for this limit, if you were to plug in the number, you would get 0 over 0, or you get infinity over infinity. And in the past, we had to do a bunch of algebra to continue. And L'Hopital's rule says that in order to find the limit, as x goes to whatever, you just take the derivative on the top, and you take the derivative on the bottom. And then find out what the limit is for that. So usually this makes it simpler. Notice this is not the quotient rule. It's just saying how fast is this function going? That's the derivative. How fast is this function going? That's the derivative. So that's L'Hopital's rule. And then let me show you a few examples with that. So for example number 1, if you have the limit as x approaches 4, and on the bottom, I'm going to put x minus 4. That is going to cause the bottom to become a 0 if I plug in the 4. And on the top, x squared minus 16. So a few weeks ago when we would do the derivative, this is actually coming from the definition of the derivative. And then we would need to do algebra. And L'Hopital's rule says, well, if you plug in a 4, this is going to be 16 minus 16. So that's 0 on the top. This is going to be 4 minus 4, so that's 0 on the bottom. So you can use L'Hopital's rule. And usually I just write down this to say that I'm using L'Hopital's rule. and it's still going to be the limit as x approaches 4. Then take the derivative on the top, which is just going to be 2x. The derivative of this 16 is 0. And then take the derivative on the bottom, and the derivative of x is 1. And now when I plug in the 4, there's no more division by 0. It's just going to be 2 times 4 divided by 1, or in other words, just 2 times 4, and it equals 8. So that's very nice. It cuts down on a lot of work for finding limits. And then I want to do a couple more with L'Hopital's rule. So for example number 2, take the limit as x approaches infinity. And suppose we have 10x squared plus 7x plus 1, and then 2x squared minus 3x plus 5. So if you substitute the infinity, infinity squares infinity, so the top is going to equal infinity. The bottom is also going to be infinity. So this is of the form infinity divided by infinity. So that means that you can use L'Hopital's rule. And then watch what happens. So when you take the derivative on the top, the derivative here is going to be 20x. And this derivative will be plus 7. The derivative on the bottom, this is going to be 4x. And the derivative here is going to be a negative 3. So minus 3. And if you substitute infinity, 20 times infinity is infinity. 4 times infinity is infinity. So that means we get infinity over infinity again, which just means you redo L'Hopital's rule another time. But basically it's taking a problem that's more complicated, that has an x squared, and then simplifying it. And when I do L'Hopital's rule again, it's going to simplify it even more. So the derivative on the top would be just a 20. The derivative on the bottom would just be a 4. And it simplified it for us even more, so 20 divided by 4, that's 5. And that is finding the horizontal asymptote. So I don't know anything else about this function, but I know at 5 that there would be a horizontal asymptote, and that the function, I don't know exactly what it would look like, but this original function, by doing L'Hopital's rule, it's saying that that function, as you follow the graph out to the right, it's leveling off at a height of 5. So this is telling us the horizontal asymptote, sometimes just abbreviated HA for horizontal asymptote. So that red dotted line is at y equals 5. So there's 2 more that we need to do with L'Hopital's rule, and one is with an e function. So for example, number 3, take the limit as x goes to infinity, and then it's got x squared on the top and e to the 5x on the bottom. So if you were to substitute infinity, infinity squared is infinity, e raised to infinity is also infinity. So this one is infinity over infinity, which means we're allowed to use L'Hopital's rule. So take the limit as x goes to infinity, and take the derivative on the top, that's a 2x. And now take the derivative of the e function, which is the e function. And because of the chain rule, I have to take the derivative of 5x and multiply by that 5. And just like with the last one, we get to do L'Hopital's rule twice, because when I take the infinity, 2 times infinity is infinity. This is still infinity, so this is still infinity over infinity. So use L'Hopital's rule again. And when I take the derivative on the top, that's just going to be the number 2. And when I take the derivative on the bottom, the derivative of the e function is the e function. And it had this extra 5, which I copied down. And then because of chain rule, the derivative of this 5x is going to be another 5, so put a second 5 out there. And now this one is essentially of the form 2 divided by infinity, which is totally different than infinity divided by infinity. So when it's a constant 2 that's getting divided by a bigger and bigger number, the result is so small that it's 0. So this one, the answer is 0. And then that is telling us there is a horizontal asymptote where y equals 0. So that means it's the x-axis. So I don't know exactly what this function looks like, but basically as you follow it to the right, it's just going to get smaller and smaller and smaller, but never cross the x-axis. So this one has a horizontal asymptote of y equals 0. Okay, one more with the L'Hopital's. So basically with this last one, I got a constant on top divided by infinity. And then what about, for example, number 4? So it's going to be the limit as x approaches 5, and then x minus 5 is on top, and x squared minus 25 is on bottom. So if I substitute 5, this is going to be 0 on top. If I substitute 5, this is going to be 25 minus 25, so it's 0 on the bottom. So that means I am allowed to use L'Hopital's rule. And then the derivative of this x is just a 1. And on the bottom, the derivative of x squared is 2x. And then this, like the last one, is going to be a number divided by infinity, and then that goes to 0. So this one would equal 0. Now take the same problem, except reverse the roles. Put the x squared minus 25 on the top and put the x minus 5 on the bottom. So basically it's going to give us the same thing as this, except it's going to be a 2x on the top and a 1 on the bottom. And then when you substitute the 5, it gives us a 10. So the order of what's on top and on bottom definitely does change the answer. Sometimes you can get a 0, sometimes you can just get a nice number like 10. Okay, then on to the main idea of this section, which is the curve sketching, like that very first idea that I talked about. So for example number 5, suppose the function is y equals x squared minus 6x plus 4, and then I just randomly chose an interval that it's from 2 to 7. So first of all, for the domain, well, with domain, you just look for places where the function is undefined. And that would be two things. Is there division by 0? This doesn't even have division, so that's not a problem. And then square root of a negative. And this has no square roots, so the domain is all real numbers. And then what about the x-intercepts? So with some of this stuff, we can use the calculator. With some stuff, we definitely need to use the algebra/calculus. Let's see with this one. X squared minus 6x plus 4. And then I'll just go to zoom standard. And it should be a parabola. Yes, it's a parabola. And there's two x-intercepts right here and right here. So if I use second calculate and ask it where does it equal 0, because that's the x-intercept, this one is between 0 and 1. And my guess it's like a 0.8 or so. So on the left, tell it start at 0, go to 1, and my guess is a 0.8. And it says that it's x equals, looks like right now my calculator is in 4 decimals, so I'll just go with that. X equals 0.7639. And then let's find this one. So that's 1, 2, 3, 4. So this one is 5 point something. So look between 5 and 6. And my guess is 5.2. Actually, that was a pretty decent guess. X equals 5.2361. Okay, there's the x-intercepts. And for the y-intercept, that just means when does it cross the y-axis. So right here, that means x equals 0. So I can just trace, plug in x equals 0, and then that's where y equals 4. So for the y-intercept, that was y equals 4. And you do have to watch out on the homework because they might just say y equals and then this is a blank, or they might ask you to write it as a point. So the calculator is saying that would be 0, 4. All right, so we have those things which actually don't use calculus. Now on to the calculus part. So where's the function increasing? And where's the function decreasing? So increasing means that the derivative is positive. Decreasing means the derivative is negative. So we definitely need to use the derivative. Y prime equals. So the derivative here is going to be 2x. And the derivative of minus 6 is just going, of minus 6x is just going to be minus 6. And then set it equal to 0, because what separates the positives and the negatives is 0. And then I could just add 6 to both sides. So this is going to become a positive 6 on the left. And then to solve for x, just divide by 2. And 6 divided by 2 is 3. So where it reached the bottom of the graph down here, that's where the derivative equals 0. So that should be when x equals 3. And then that is even the minimum point. So I'm even going to write that down over here. The minimum is at 3, negative 5. And then this side is decreasing. So for the decreasing part, so that's from negative infinity until it gets to where the x is 3. So from negative infinity to 3. And then for the increasing part, that would be from here to there. Well, not there, I mean forever. So increasing from 3 to infinity. Okay, now on to another example, and one that has a fraction. So in the homework they like to do fraction ones, and the reason is because then there's going to be the vertical asymptotes. So how about if we've got y equals a 5x divided by x squared minus 16. So for the domain, if you put the bottom equal to 0, that would cause division by 0 and it would be undefined. So in other words, x squared minus 16 cannot equal 0. And then add 16 to both sides. So I get x squared equals 16. And then take the square root of both sides, and when you do, don't forget to put plus or minus because there are 2 answers. And I forgot to cross out my equals. So x cannot equal plus or minus 4. So if they ask for the domain in interval form, then that means that basically we've got a negative 4 right here on the number line and a positive 4 right here. And the domain would be all of this, but not the negative 4. The middle part, but not the positive 4. And then the right side. So that would be from negative infinity to negative 4 is the left side. Union, the middle part from negative 4 to positive 4. Union, and the right side from 4 to infinity. So there's the domain. That also means there's going to be vertical asymptotes. So there's going to be vertical asymptotes at x equals 4 and x equals negative 4. So basically that means there's going to be a dotted line in the graph here and a dotted line on my sketch. And then what about horizontal asymptotes? Well, for horizontal asymptotes, that was the whole idea of L'Hopital's rule. So take the limit as x goes to infinity, because that's basically saying what happens to the graph as you go out to the right, of our function 5x over x squared minus 16. And this is of the form infinity divided by infinity, so you can use L'Hopital's rule. And the derivative on top is just going to be a 5, and the derivative on the bottom is 2x. And then this is the form where you have a number, and this becomes infinity. So this becomes 5 divided by infinity, and 5 divided by a very large number is so small that it goes to 0. So for the horizontal asymptote, I would say y equals 0, or in other words, the x-axis. So that means when I finally do take a look at the graph, it's going to go down like this and get smaller and smaller and smaller. Okay, now we need to see where it's increasing and decreasing. So I need a new page, and just to remind myself, it's 5x over x squared minus 16. All right, now for the derivative. So for this, I need the quotient rule. And the quotient rule starts on the top. You take the derivative of 5x, which is just 5, and then just copy down the x squared minus 16 part. The next part of the quotient rule goes minus. Now just write down the 5x, and then take the derivative of this, which is going to just be 2x. And then the bottom gets squared. And because I already put the bottom equal to 0 on the last page, I don't have to do that again. All I really need is, when does the top equal 0? So even though it looks like this is a mess, we already did this work, so we don't have to redo that. We just need to do the top. And on the top, if you distribute, this is going to be 5x squared. And then 5 times 16, I think that's 80. Let me double check. 5 times 16, yes, that's 80. And I'm going to change my calculator back to 3 decimals. I prefer 3. Okay, so it's 80. And it does have a minus sign, so minus 80. And then this, when you multiply these two, that's going to be minus 10x squared, and then we're setting it equal to 0. So if I put the x squares together, in total, that's going to be negative 5x squared. So negative 80 minus 5x squared equals 0. And then if I move the 80 to the other side, it's going to become a positive 80. And then divide both sides by -5. And this is going to be a -16. X squared equals a -16. And when you take the square root of both sides, this is an imaginary number. So the square root of a negative is imaginary number, and when we're looking at the graphs, we do not have any imaginary numbers. So we don't use imaginary numbers. So for this, you could just say that's an imaginary number, or you could say no solution. All right, now let's put it together and take a look at the graph. When you graph, make sure that you graph the original function, not the derivative. So on the top, there's a 5x divided by, put the bottom in parentheses, so that's x squared minus 16. And then take a look at the graph. So there's vertical asymptote and there's vertical asymptote. And notice that when I did the derivative, I got the derivative does not equal 0. So that means that there are no minimums or maximums. And also, this is decreasing, this is decreasing, and this is decreasing. So there's also no place where it changes to increasing. So on the homework, they would say any possible minimums, any possible maximums, and then these, there would be none. And then for decreasing, so basically it was decreasing except for this -4 because it's undefined there, and this is decreasing except for the +4. So basically the way that I wrote the domain, this right here, that's also the answer for where it's decreasing. So the left side of -4, the middle part between the -4 and +4, and then the right side from 4 to infinity, that's where it's decreasing. And there's no place where it's increasing. All right, now one more. So this is example number 7. And it's going to be y equals x plus 1 over x. As far as the domain, this has division. That means that the bottom cannot equal 0. So the fastest way to say it is x cannot equal 0. Or if you look at a number line, this has to be thrown out, but I have to account for the left side and the right side. So in interval notation, that would go from -infinity to 0, and then also the right side from 0 to infinity. So there's the domain. And then what about x-intercepts and y-intercepts? So we've got y equals an x plus 1 divided by x. And does it cross the x-axis? Does it cross the y-axis? And it looks like it does not touch either axis. It's definitely not hitting the x-axis. And even though the calculator looks like it's hitting the y-axis right there, well, this right here is where x equals 0. And if you plug in a 0, it's undefined. So there's no x-intercepts and no y-intercepts. So no x-intercepts and no y-intercepts. So basically, even though it looks like the graph stops right there, that's just because of the pixelization on this calculator. It actually looks more like this. So it looks like right there, there's a minimum point, and right there, there's a maximum point. And then this would be increasing and then decreasing. This would be decreasing and then increasing. So this point right here and this point right here are definitely important. And both of these places are where the derivative equals 0. So next up, the derivative. So the derivative of x is just 1. And then this is one of the ones that I have on the 3x5 card, which I don't have with me right now, but luckily I remember the derivative of 1 over x is negative 1 over x squared. And then set that equal to 0 so that we can find these 2 points. So the next thing I would do is I would take this negative term and move it over to the left side so it becomes positive 1 over x squared. And then to clear out this fraction, I would multiply both sides by x squared. On the left side, it would only leave 1, and then on the right side, it would only leave x squared. And when you take the square root of both sides, it's going to be the square root of 1, but you do need to put the plus and minus 1. So this must be x equals negative 1, and this must be x equals positive 1. And then I can find the actual minimum and maximum point. So if I go to trace and I plug in the negative 1, then that says it's at negative 1, negative 2. So that's this, which is actually a maximum point. So there's a maximum at negative 1 comma negative 2. And then for the minimum, so that's going to be this point when x equals a positive 1. And I'm pretty sure the graph is symmetric. So if this is negative 2, that's positive 2. Let me just double check trace and plug in a 1. And sure enough, it is y equals a 2. All right, then the last part on this one is where is it increasing? So this left side is increasing and this side is increasing. So for increasing, that would be the left side from negative infinity until negative 1. And then also this from 1 to infinity is increasing. For decreasing, that would be this little red part right here. So that's between negative 1 and 0. And then this part is decreasing. So that's from 0 to 1. All right. Now there's one last piece that I want to add, because they do add this on the homework, is what if they said from the beginning, look at it from negative 3 to positive 3. So we've done almost all of the work, except now change the window so that x goes from negative 3 to positive 3. And then look at the graph. So we're basically just zooming in on the graph. And then you do need to test these points at the end. So if I trace and I put a 3, so sometimes this point right here would be the tallest point or perhaps the shortest point of the whole graph. But this one goes taller up here and it actually goes lower over here. So this is neither a minimum or a maximum. And if you also check the negative 3, then there's places where it's taller, so that's not the maximum, and there's places where it goes lower, so that's not the minimum. But there are times when you would graph it and they would say go from negative 3 to positive 3, let's say, and then you had found out the derivative equals 0 down here, and you found out the derivative equals 0 right there, and then at the end, the graph, by the time you look at where the 3 is, then this is a minimum, and this is actually the very lowest it ever goes, so it's called the absolute minimum. And then perhaps by the time you get to positive 3, there's this point right here that's taller than any of the other points, then this is called an absolute maximum. All right, so that's it for this. I'm now going to just take a quick pause and then bring out some homework questions.